In this video, I'll be talking about electric field due to parallel conducting plates by using the Gauss law. So in the last video, I talked about the same thing, but rather in a different approach, where you just find out the electric field between the two plates is this, sigma over epsilon naught. But now, here I will be using the Gauss law and inside the plates. So let's say you have a point. Let me erase this one first. Let's say we are interested in finding out the electric field at this point, P, at this point. In order to find out the electric field at this point, we're going to draw an imaginary, the Gaussian surface. This is the imaginary Gaussian surface, and this is the point P. This is the point P. The electric field direction due to this positive charge is away. This is the electric field direction. And again, due to this plate, due to this negative plate, the electric field direction is again still this way. So the total electric field direction is only coming out of the plate. So this is the total electric field direction. So the electric field doesn't matter from which plate, from positive plate or negative plate, the electric field direction is this. And if I look at the area vector, let's say this is the electric field, and the area vector is also in the same direction. But now, if you look at this point here, the area vector is this way, and the electric field is this way. So no flux is coming out of this region. There is no flux. The only flux that is coming out is only along this direction. Okay, and let us assume the cross-sectional area of this circle is A, and sigma is the surface charge density. Sigma is surface charge density. If sigma is the surface charge density, that means how we can find out the total charge enclosed by this Gaussian surface. The total charge enclosed by this Gaussian surface is simply equal to the sigma, surface charge density, times the area. This area is the area of this circle here, this cross-sectional area. That's the total charge enclosed. And I have written down all the information right here. If you need to take a look at any point, all the information are here. That's the total charge enclosed by the Gaussian surface. And now let's apply the Gauss law. This is the Gauss law here. What does this term tell you? This term tells you the total electric flux passing through the Gaussian surface, through this Gaussian surface. And this E vector, again, remember, this E is the total electric field. It's not due to only one charge plate, it is due to the total. And this one is a constant. Here we have assumed these two plates to be infinitely long plate, and the reason is, if it is not an infinitely long plate, then there could be some fringe field that may add up this electric field. There could be some fringes field. In order to avoid the fringe field, we have assumed this to be infinitely long. If this is infinitely long, then the contribution due to the fringe field will be very, very minimal, almost negligible at this point. And that's the reason we assume these two plates are infinitely long plates. Okay, so the electric field, so the only flux that is coming out is from this region. So how do you find out the total flux? The E vector times the area vector, and it is constant over all the region. So we have E times A, and the charge enclosed by the Gaussian surface is sigma times A, and this is the permittivity of the medium, or the permittivity of this medium. So if we just solve for the electric field, what you get is sigma over epsilon naught, which is expected because it should be the double of the electric field due to one charge plate. If you have only one charge plate, the electric field is sigma over 2 epsilon naught. Now if you have two charge plates, the positive and negative, then in between the electric field is doubled. That's what we see here, sigma over epsilon naught. And also one important point is it is independent of the distance. It doesn't matter where you measure, whether you measure here, 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 any point between the plates, you will get exactly the same electric field, sigma over epsilon naught. And the other thing to remember is the electric field direction is always from positive to negative, from positive plate to negative. That this is the direction of the electric field, from positive to negative, positive to negative. This is it. If you have